So as you can see from the text above, when an object travels fast, and we're talking significantly fast, as in 10 to 20% the speed of light, all the way up to 99.999% the speed of light, time and length of the object change, because time and length are relative to speed. We don't notice this going at slow speeds that we would go on Earth, such as 100 kilometers an hour, because it's not fast enough to delay time or to stretch length. So what we have is an astronaut whose pulse is constant at 72 beats per minute on Earth is set on a voyage. What would the pulse be relative to Earth when the ship is moving at 0.10 c, or 10% of the speed of light? Well, we are looking at time, but we've been given actually the frequency, 72 beats per minute. Now, the key thing in any of these questions is to determine whether this is the frequency for a stationary observer or for a moving observer. The person observing the heartbeat would be the astronaut themselves, so this would be stationary compared to the observer. So the frequency would be 72 beats per minute. And the time interval is defined as 1 over the frequency, how long it takes one beat to happen. So 1 over 72 should be 0.014 minutes. We know the speed that this astronaut is traveling at is 0.10 c. And we're trying to find the time compared to somebody who is in motion observing this. And now I know you might be thinking, well, the observer of this is on Earth. This is how it appears to the person on Earth. The person making the observation is stationary, so somebody on Earth would be in motion relative to the observer. So to determine this, we go to the time dilation formula. Substituting in what we know, delta TS, 0.014 minutes. Now, we don't actually know V. We do not need to go and calculate it out in terms of an absolute number. We can plug it in as 0.10 c, and because it's V squared in the formula, that will be squared. Forgot one small thing here. Plug it in as 0.10 c, which is squared over c squared. Working this out, (0.10 c² is 0.10 c times 0.10 c. So working that out, we would get 0.01 c² over c². And what we can do at this point is we can cancel the c²s. Which will give us under that root 1 minus 0.01. On the bottom, we get the square root of 0.99. And we can put this in a calculator, work it out. We need 2 sig figs. We get 0.014 minutes. To find the actual pulse frequency, just like when we define the variables that delta t equals 1 over f, f equals 1 over delta t, so 1 over 0.014, which would still work out to 72 beats per minute. Now, why does it work out the same even though this person is moving significantly fast? Well, it turns out that even 10% of the speed of light isn't fast enough to cause a very noticeable change in time. We need to be moving even faster. So what if this ship was moving at 0.90 c, 90% the speed of light? Well, we would have basically the same calculation. Except now, our V 0.90 c. Working that out, .90 all squared is 0.81 c squared. Cancel the c's. We get on the bottom the square root of 1 minus 0.81. Which will give us the square root of 0.19. Calculating that out, going to 2 sig figs, gives us 0.032 minutes. Clearly we do have a time change now that we're going at 90% the speed of light. To calculate the actual frequency of this heartbeat, again, frequency equals 1 over time. Should be 1 over 0.032. Going to 2 sig figs, now it appears as though this astronaut's heart is beating at 31 beats per minute. So time has clearly slowed down now that we're going this fast. And the faster we go, the more time will appear to slow down.